Discovery, go at throttle up.
Okay, this is the O3b MPOWER 7-8 mission launching on a Falcon 9. Hello, everybody. I am EJ, your host
at SPACEX.
of this, and yeah, the cast just cut in. We're looking at a Falcon 9 launch here out of 39A. O3b MPOWER is satellites for SES, if I'm remembering correctly. It's an SES-owned O3b networks. There's 2 payloads on board today, and this Falcon 9 that's launching is booster 1090 on its first flight. First flight. Whoa! Hold on. First flight. Look at, dude, it's clean. Look at it.
There's a photo from the day the payload was encapsulated in the fairing.
Is that John?
The fairing's made up of carbon fiber composite materials, and it protects the satellites on their way to orbit. The fairing is made of the 2 halves that you can see here.
Wow, that's just great.
High-pressure gas at approximately 3 minutes and 25 seconds into flight. Now, both fairing halves supporting today's mission are flight-proven.
Look at how clean it is.
One half flying for its 22nd time, the other's flying for just its 2nd time. And both halves of the fairing will be recovered once again after today's flight by our fairing recovery ship, Bob. Below the payload fairing, we have the 2nd stage. That's the part of the rocket that will take our payload to its destination orbit today. The 2nd stage will ignite its single Merlin vacuum engine, or MVAC for short. That comes about 2.5 minutes into the flight, and we'll burn that engine twice more after that before we deploy the satellites. Below the 2nd stage is the 1st stage, which is flying for the first time today, and the lack of soot on those white propellant tanks highlights the newness of this stage.
Newness.
Now, the 1st stage has an engine section, propellant tanks, and the inner stage.
Or,
I think, see the inner stage at the top of the 1st stage, and it's prominent with a black thermal protection system. And at the very bottom of the 1st stage, that's the engine section where the 9 Merlin engines are installed inside the Octaweb thrust structure. Following the 1st stage burn and main engine cutoff, the stages will separate from one another. The 2nd stage will continue to orbit while the 1st stage will start making its way back to Earth. And after it's recovered, the 1st stage goes through a short refurbishment to get it ready to fly again.
No problem.
Now, today we're attempting to land the booster on our drone ship. Just read the instructions. That's currently shown there, stationed out in the Atlantic Ocean, about 650 kilometers east from the launch pad 39A. If we're successful in recovering the booster, it will mark the 385th successful recovery of an orbital class rocket. Finally, back at the launch pad, we have the large truss structure next to the rocket. That's part of the transporter erector, or TE. We use the TE both to roll the rocket out to the pad and to raise it to its vertical launch position. The TE also routes the vehicle's fluids, power, and telemetry umbilicals from the ground to the rocket and the satellites. Now, in callouts over the net today, you may hear the vertical portion of the TE that's right alongside the rocket. That's referred to as a strong back by the launch team. Now that you're a little more familiar with the vehicle, let's learn more about today's payloads.
Want to watch a rocket launch with Daddy?
In a world where change is faster than ever before, the pace of innovation is evolving and accelerating. To support the era of digital transformation, artificial intelligence, and hyperconnectivity, the intelligent systems that enable all of this progress.
One man will launch a satellite. Yep, we got beautiful Titan emotes now.
Demands for high-performance network services.
All right.
At SES, innovation is part of our DNA.
Took you long enough? Shut up!
It drives us and helps us to bring new stories to life. And our our O3b.
I don't remember the last time we saw a new first stage launch.
The next pair of O3b MPOWER satellites is ready to travel through space to join our medium Earth orbit satellite constellation, 8,000 kilometers away from Earth's surface, and help continue delivering high throughput, flexible and reliable network services across the globe. With our O3b MPOWER system becoming operational.
That's probably going to get claimed by YouTube, so we won't listen to that. Middle East, Latin America, oil rigs, people taking a selfie, hurricanes, tablets, military people doing work, ports, lady on a tablet, satellite constellation, connecting people, circular building with parking lot. Guy talking about how much his satellites are amazing. Seriously though, it will demo, like, corporations use a lot of like demo music, and yeah, it gets claimed all the dang time. Look at this satellite. People building it. It's awesome. Guy must be Italian. He's with his hands. I thought that was Bill Murray. Is it still playing music?
Of capacity, which means we can do more services. With this constellation, we're able to connect remote islands. We're able to connect enterprises that have remote locations to their central compute.
Oh yeah, O3b MPOWER is the Starlink competitor, by the way. Yeah, I forgot to tell you guys that. We need more EJ voiceover. I need a weapon. Right this way. How do they make sure the rockets don't hit satellites on their way up? Xanax, you know how the FAA kind of stops, like prevents launches from happening and stuff?
Discovery, go at throttle up.
Yeah, that. They've debris mitigation and a clear launch corridor, make sure there's no traffic in the ascent corridor. Yeah, that's all. Yeah, I mean, it's up to the companies with trajectory optimization, and then the FAA approves it, approves the flight plan. There's 2 satellites on board, Hokie. This is a MEO constellation, so 8. There will be 8 in the constellation at MEO.
And right now we're getting ready for the call out that strong back retraction is
underway.
There it is. Now that means the clamps around the second stage will be beginning to open. The hydraulics will open them, and that's a process that takes about 20 seconds. And the strong back is that vertical structure, as we mentioned, of the transporter rector, and that carries propellant, electrical, and gas up to the second stage and to the satellites. You can see the clamp arms are coming open.
Oh, hold on a second, dudes. Watch the clamp arms open, and also check out the cranes that are disassembling Starship's launch pad out there, or old launch pad. They already got all the pipes out of there. And there's pieces of the old LOX tank. Check this out. Breaking from Adrian. Take a look. Today, the FAA issued a license modification authorizing SpaceX to launch multiple missions of the Starship Super Heavy vehicle on the Flight 7 mission profile and vehicle configuration. The FAA determined SpaceX met all safety, environmental, and other licensing requirements for the suborbital test flight. The FAA continues to increase efficiencies in our licensing determination activities to meet the needs of a commercial space transportation industry. The license modification that we are issuing is well ahead of the Starship Flight 7 launch date, and is another example of the FAA's commitment to enable safe space transportation. Flight 7 mission profile involves the launch of a combined Starship Super Heavy vehicle from Boca Chica, Texas, a return to launch site of the Super Heavy booster rocket for a catch attempt by the launch tower, and water landing of the Starship vehicle in the Indian Ocean west of Australia. Please contact SpaceX for information about its planned launch date. The SpaceX Starship program operates under FAA-issued Part 450 launch licensing. Whee!
Inside T-minus 2 minutes, we'll hear a similar call out that stage 2 liquid oxygen load is in closeout. That means it's complete. And at that time, the first and second stages will contain nearly 1 million pounds of kerosene fuel and liquid oxygen. You can see the white clouds right now around the vehicle. That's formed as the chilled gas above the liquid oxygen tank.
Next flight survey slab.
So we are now fully loaded. As I mentioned, the clouds that you can see around the vehicle, that's the gas above the liquid surface in the tanks, gets chilled down, and when it's vented overboard to maintain pressure in the tank, that means that chilled gas comes into contact with the warm, moist Florida air, and it condenses the water in the air to form the clouds that you see on your screen. Next major activity will be T-minus 60 seconds. That's when Falcon 9 will be in startup. The rocket's autonomous internal flight computers will have taken over the launch countdown. The call out you just heard now, ground gas closeouts. We're venting down the lines on the strong back, make sure that they're empty before the Falcon 9 lifts off. As we get into the final minute, the terminal sequence inside of T-minus 2 seconds will light the Merlin engines. But right now, as we wait for the call out at T-minus 1, everything continues to be go for launch.
We are go for hamster.
Falcon 9 is in startup.
Falcon flight computers now controlling the launch vehicle. Ground computers are doing the last steps here for ground systems.
Hampus, I don't know what they're going to do here.
Go for launch.
We can talk about it during Space News.
That should be the last call out. The SpaceX launch director gave the go for launch. We're coming up on the T-minus 35 second mark. Everything is go. Let's listen in to the launch of Falcon 9 with MPOWER E.
30 seconds. Falcon 9 has entered startup 30 seconds ago. It's definitely John, guys. He did not retire.
T-minus 15 seconds. T-minus 10, 9, 8, 7.
Sound suppression water system is on.
4, 3, 2.
Ignition.
1. Ignition and liftoff.
Liftoff. Second Falcon 9 of the day. O3b MPOWER. 7 and 8 satellites going to medium Earth orbit on a brand new Falcon 9.
Chamber pressure is nominal.
No, John has not retired. It was speculation, Forge.
T-plus 30 seconds, and Falcon 9 has successfully lifted off from Complex 39A at Kennedy Space Center. We're carrying the two O3b MPOWER satellites. We've heard the initial call out. Stage 1 propulsion is nominal, and the Falcon 9 is beginning the pitch downrange.
Telemetry nominal.
Power and telemetry is good.
Avionics
should get a call for supersonic.
Power and telemetry coming from the second stage are nominal on Falcon 9. We're into the throttle bucket right now.
Falcon 9 is supersonic.
There it is.
We've heard the call. We're supersonic.
Whoa. Woof.
And engines have throttled back up as we're coming through the period of maximum dynamic pressure. Guidance officer calls out Max Q, confirming we're through the period of greatest stress. 9 Merlin engines running at full power.
This is
now on your screen, you can see on the left the speed and the altitude of the first stage. Stage separation will occur at about 8,200 kilometers per hour. And in order to get into the initial orbit, what we call the parking orbit, the Falcon 9 has to gain enough speed to reach about 27,000 kilometers per hour. That's a bit under the 17,000 miles per hour, used as a rule of thumb for the low Earth orbit velocity. Now we've got several events coming up in about half a minute. We're going to have main engine cutoff. Then a few seconds later, we get stage separation. And then the second stage engine start number 1 called SES-1. During main engine cutoff, we're going to shut down the 9 Merlin engines, then we'll get the stage separation. And once we're separated,
look at how clean it is in the interstage.
In daylight, you should be able to see the view of the first stage as we begin a slow flip to orient the first stage back towards Earth, while simultaneously the MBAC engine on the second stage will ignite for the first time.
Miko. Stage separation confirmed.
Good staging. Watch, it's going to deposit some soot right here. Ready?
Evacuation.
First stage, you could see it pulsing its thrusters to basically make sure it doesn't get perturbed too much from the
We've got
second stage
successful
exhaust.
main engine cutoff, stage separation, ignition of the second stage engine. Nice views late in the afternoon as we're leaving Florida, and maybe even a little bit of the contrail visible in the distance behind the second stage nozzle. And on the left side, you can see the first stage.
I know, Forge. I just saw it.
Coming up now is fairing separation, about 5 seconds.
That was a brand new booster, mate. Yeah, Flight 1. There's a shot of the payload attachment fitting.
Fairing separation confirmed.
Well, we saw in the background the fairing
There's a little
separate.
bit of a fairing there.
As we had mentioned at the start of the webcast, the payload adapter we use for the MPOWER satellites blocks the view of the camera, which is one reason the webcast will be ending once the first stage lands and the second stage gets into its parking orbit.
Vehicles are on a nominal trajectory.
GNC with the right call out, we're on nominal trajectory.
L-124 launched this morning,
Alto. 4 minutes
Alto.
into today's mission.
I covered that too.
Now, as I mentioned, if we were bringing the first stage back to a land landing, we'd do what we call a fast flip. That would quickly turn the stage around. But we're going downrange to the drone ship, so we do a more leisurely flip, and it's not quite as fast as we would do for a land landing. In fact, you can see the stage is slowly rotating. It's moving at a speed less than 1 degree per second. Now, coming up in 2 minutes, we expect to have views of the first stage's entry burn. And in the entry burn, we'll relight 3 of the M1D engines on the first stage. We start with the center engine, what we call E9, and then we follow it up shortly afterwards with engines 1 and 5. And that'll slow down the vehicle as it gets ready to pass back into the Earth's atmosphere. Now, we need to slow down in order to reduce that re-entry heating, and that ultimately helps us to recover and reuse the first stage. Now, if you've been
thermally
watching
conditioning
on
the
left
engines,
side, you'll notice the altitude of the first
restart.
stage has reached its peak. I think it got to about 123 kilometers, and now it's beginning
notice
to
the
trip
vents
back
only coming
down
out
to
of
the
one
Earth's
side.
surface.
See?
Now, it took us about 2 minutes
there's
from
an engine
stage
there being
separation
chilled,
until
middle
the first
engine, and
stage
then the other
reached
engine
its
over there.
maximum height. And it's going to take us another 2 minutes to come back down to the altitude where the entry burn begins. Now, this portion of flight is in the vacuum, and you can see the grid fins on the first stage view from the interstage camera. Not right now, we're looking on the inside of the interstage, but on the outside, you can see the grid fins. They don't have a function right now. They're deployed, but there's no atmosphere for them to react with. The grid fins come into play after the entry burn once we start to bite into the Earth's atmosphere.
It is, Hokey. It's definitely
now, during
perturbing
the entry burn, Falcon 9 is going to be decelerating by
but the
firing
pulse
its Merlin
modulation is
engines,
very,
but
very
it's
low
not
on those
slowing down
ACS.
all that much. It's bringing it somewhat down. But that means that we're going to fly through Merlin's exhaust gases, what we call the rocket's plume. And that's what deposits that layer of soot on the vehicle tanks, which is why our flight-proven vehicles look so sooty. That comes from the fuel that Falcon 9 uses. Coming up in about 10 seconds, we should have entry burn.
My
Wait
favorite
for the
part.
call out, see if we can spot it on the camera.
Guys, I'm not talking because John Innsbrucker the guy that's commentating is a way better commentator than me, so I'm just
Stage 1 entry burn startup.
shutting up, dude. Supersonic retro propulsion.
Entry burn's begun. The center engine is lit. That's kind of the circular plume. And now engines 1 and 5 come in, and that's why the plume changes shape that you can see on your screen.
I'm just being quiet, man. I usually provide more insightful commentary, but
waiting for entry burn shutdown.
It's a treat hearing this guy commentate on launches.
Stage 1 entry burn shutdown.
On time, we've got shutdown.
Now watch, the grid fins will start moving now.
Entry burn looks good. So now that we've completed the entry burn, the first stage begins entering the Earth's atmosphere. Now the maximum deceleration is going to happen in about 15 seconds. The first stage will experience about 5 Gs. But because we perform the entry burn, this portion of flight is not as difficult for the first stage. If we didn't have the entry burn, the first stage would have a tougher time coming in for the landing without compromising reusability. And reusability is key to lowering the cost of
Stage 2
spaceflight.
is internal guidance.
Coming up next,
Best
we have
commentary
internal
ever.
guidance on second stage. We're now controlling the angular momentum state of the second stage. We're going to get MVAC engine shut down in about 20 seconds. And then right after that, we should get into the landing burn sequence on first stage. Reminder, the first stage
Stage 2 FTS has
is targeting a drone ship landing. out in the Atlantic Ocean.
John's the best.
Waiting for the call out for SECO.
Back shutdown.
Nice shutdown. Not a lot of nozzle weeble wobbles.
We've got MVAC engine shutdown.
First
Nominal
stage,
parking orbit.
really getting
Stage
into
one
the
landing
heavy
burn.
arrows. You see it moving
And
around.
both call-outs right on time. Guidance reports a nominal parking orbit for the second stage. The first stage has begun the landing
There's
burn.
the drone ship.
Headed to the drone ship on the power of the center engine E9.
Stage 1 landing leg deploy.
When the landing legs deploy, the grid fins freeze up. It's just on thrust vector control and attitude control to plop Falcon 9 successfully down onto the
Stage
drone
1
ship.
landing confirmed.
All right, and we have touchdown.
Easy peasy.
Formerly new booster on the first on the drone ship out in the Atlantic.
So cool.
So
I'm
there
sorry,
you
man.
have
I've
it.
watched hundreds
That
of these. I don't
landing
care.
marks
It's so
SpaceX's
cool.
385th recovery of an orbital class rocket. That includes first stage landings for both Falcon 9 and Falcon Heavy. Meanwhile, the second stage,
That cable
there's a
management,
great
though.
view, and I think in the distance you can see a little bit of the contrail in the upper atmosphere as we headed east out of the Cape.
That's
Just
sick,
before sunset.
dude.
And so we're watching the last glow of the sun as the second stage heads eastward.
Did you see that?
Into
Did you
the
see how it
shadow of the
expanded
Earth.
over time?
So second stage embarking
It's
now
awesome,
on the initial
dude.
coast phase. The view
It's a
you're seeing there,
jellyfish
that's
from
the payload
orbit.
adapter. The MPOWER spacecraft are just on top, but they're hidden from view. And so with that, we're not expecting to have great views of payload deploy, and we're going to end the webcast at this point.
Dude.
But keep an eye out on our exit.
Here, hold on. I'm pausing it for a second. Ah, come on. Bring it back. Bring it back. Bring it back. Back it up. So check this out. That's the ascent right there. And you see, that's first stage. Right there is staging. When the plume really starts expanding out, that's when you get to your staging because of the difference in the nozzle, and the ambient pressure is a lot lower when the second stage fires its engines. So because of the low pressure and because of the different nozzle, this bell shape right here, you're going to get the plume is going to propagate in a very, very different way. That's why it looks kind of squiggly here, and then it just kind of fans out. That's second stage ignition right there. You could see it in the contrail. It's actually super freaking cool. The only reason why we could see this right now is because the sun's going down. And the sun's light is illuminating. It's backlighting the plume. So you could see it. Really, really cool. Good question here for the audience. Why a bigger nozzle? You need a bigger expansion ratio. Basically, the plain English way of saying it would be to get the gases to go where you want in the vacuum, because it's really easy to just have them just go everywhere. It's just additional nozzle to make sure that the gases are accelerating out in one direction, because when you're up in the vacuum, there's nothing that makes those gases just go in a straight line. Basically, how the gases like to come out of the rocket engine when you're up in the vacuum is like if you put your thumb over a hose and shot water out sideways. There's nothing to hold that gas in one direction. Compare that to like Falcon 9 when it's lifting off. The gases are kind of in a nice column that's kind of teardrop shaped. Yeah, that doesn't happen up there. Now, the benefit of that is that there's nothing in the way for the gases that are coming out of the rocket engine. The fire that comes out of the rocket engine, there's nothing for it to hit with the second stage engine because you're in the vacuum. When you're down here, the fire stays in a nice cool column, but it also suffers from basically the atmospheric pressure pushing in on it. So basically the upper stage engine, you need a bigger nozzle to get the gases to go in one direction, but you can accelerate them out a lot faster. That's why second stage engines with the right nozzle tend to be more efficient than first stage engines. If you want to speak nerd here for a second, we're talking about a much bigger expansion ratio to make sure that your exhaust velocity gets maintained tangent to your jet, your desired, jet vector. That's probably not the right way to say that. The fire needs to go in one direction for the rocket to really go forward nicely, or else it's not going to go very far with a short nozzle. Yeah, let's get back up to live here. Oh, yeah,
this Kennedy Space Center, the Eastern Range, and the FAA for supporting today's launch. And as always, thanks to all our viewers for logging on and your continued support. Remember to follow at SpaceX.
Flow direction. Yeah, that would probably be a better way to say it. Yeah.
Thank you, and we'll see you again soon.
See you, John. You see all this, guys? See how the cables look really nice and shiny? It's EMF. They have a EMF sheathing around the cable so they don't get, well, irradiated, amongst other things. Everything is rad hardened and rad shielded on a spacecraft. That's actually cool because you get to see it up close. And yes, those are zip ties. Yep, those are zip ties. Absolutely. Yeah, they're absolutely zip ties. What? They work. So the stubby upper stage nozzle exists for design constraints on payload. That's a good question. I thought this might come up. Iger, that stubby nozzle is when lower performance is required on your second stage, right? Why does SpaceX have the stubby nozzle in the first place? What do you mean lower performance? Well, the materials that the second stage, the Merlin vacuum nozzle is made out of are actually a lot of rare earth metals. I won't say exactly what it is, but SpaceX is the short answer to this question is that SpaceX is launching so many second stages that they're exhausting certain rare earth metals for Falcon. Falcon is basically eating up the supply chains of certain rare earth metals, which is pretty funny, actually. I don't know that for sure, but I'm pretty sure that's what's going on, right? So the cut nozzle is there. You take a huge hit in efficiency, but if you're launching a smaller payload, doesn't matter. The efficiency hit isn't going to screw your delta V up that much. You know what I mean? When does space news start? Pretty much now, actually. No, not zip ties. Industrial aerospace zip ties. Big difference. Those are zip ties, homie. Those are zip ties. They're not industrial aerospace. Somebody picked red because they liked red. Those are zip ties that you get at the hardware store. You don't need to reinvent a damn zip tie, okay? It's fine. It clearly works, so. Yeah, niobium alloys. Yep. Also used in body jewelry because it's biologically inert. Till. Today I learned. Clearly from Home Depot, so because they're orange, yeah. The view of the other side of the nozzle there is it's supposed to be red hot. Yes.
This is space. I'm in space.
Hokey gifted a sub to Monev. Oh, right on. Yeah, that's supposed to be... Okay, so why is this made out of certain really rare earth metal alloys? Why is it built like that? Well, you see... Okay. It's glowing. You see that? It's glowing. It doesn't do that for fun. That's how the nozzle keeps cool. See that? That's how it keeps cool. That's really important to understand.
This is space. I'm in space.
Thank you for the resub, man. This is how the nozzle's actually radiating. To speak actually, it's radiating heat off through light. Yep. You can't use air to shed heat up in space. There's no air up there. So let's take an automobile, for instance, with an internal combustion engine. How would you keep it cool? Well, the automobile runs coolant through an aluminum or aluminum radiator. And the air that's coming in through the front grille of the car passes through the aluminum radiator and it cools the coolant, and then they pump the coolant back in. That's a way that they shed heat from the motor. You can't, that's called convection. You know, exchanging heat with gas is called convection. You can't do that here because there's no gas. You obviously don't want to conduct heat either. Conduction is heat transfer from touching something. You don't want to conduct heat into your rocket motor either here. The reason why is because your turbine machinery that's moving really cold liquid oxygen needs to stay really cold. That's why it's wrapped in Myla. Or MLI, not Mila. It's wrapped. It's got a space blanket around it. See the big space blanket that looks like a trash bag? That thing? You want to keep your turbine machinery cool. So conduction is out. Convection you can't do because there's no air. So what does that leave? Radiation. This is a passive cooling system on the engine. The engine glowing is radiating the heat through black body radiation. It's basically shedding the heat through light. Yes, that's a thing. Yes, you can do that. Yeah, lots of different types of light make heat. An incandescent bulb is a good example of this, but you're doing the reverse of that. Well, actually, not really. It's pretty much the same idea. I was talking about a part above the nozzle after the engine cut off. It's like some pipe. Right here, FlyKin, is a way to keep the inner parts of the nozzle nice and cool. The gas generator right here on the Merlin vacuum. So it is being, the exhaust from the gas generator is being dumped into a recirculation manifold that film cools the nozzle. There's basically a jet engine right here, or at least half of a jet engine. It's a gas generator. What's a gas generator? Like I said, it's about half of a turbojet. Instead of the suck, squeeze, bang, and blow, a gas generator is just the bang and blow. Okay? Like a turbojet, you gotta bring air in, you gotta compress it, and then you have to introduce fuel, atomize it, introduce fuel, and blow it out the back. What a gas generator is a jet engine that's been cut in half. There's no compressor. You don't need that. Why don't you want a compressor? There's no air up there. Once again, there's no air. It's the vacuum. So you got to find another way to keep your jet engine working. So the gas generator has a LOX and RP1, a mini LOX and RP1 injector plate in there. And it's the, like I said, instead of suck, squeeze, bang, blow, right? It's just the bang and blow part, right? And that's turning a turbine. So you basically have a combustor and a turbine. The combustor explodes, shoot hot gas over the turbine, and the turbine spins. So what's the turbine driving if it's not driving a compressor? It's driving your pumps. Yeah. Turbocharged fuel pump. Well, it's not turbocharged fuel pump. Turbocharged implies a pneumatic compressor. No. That's just a turbo pump. You want to keep that cool. Right? Obviously, it's moving cold propellants. So how do you keep it cool? Like, and I'm getting to it. How do you keep that thing cool with a gas generator? The gas generator is a jet engine, basically. It's the back of a jet engine. I don't know if you guys knew, the last time I checked, a jet engine gets hot. A little bit of a trick here in aerospace engineering. In order to keep that thing, this part, the gas generator, to run nice and cool, they screw with the mixture rate here. So what's mixture rate? So in order to get the rocket to make make the boom boom come out the back, in order to achieve combustion, you need to have fuel. You need to have fuel, oxidizer, and a source of ignition. Well, the rocket can be self-sustaining. It's really hot, so all you got to do is spray fuel and oxidizer into the fire, and it'll just make it, it'll keep going. So adjusting the amount, there's like an ideal mixture between liquid fuel, in this case RP1, and liquid oxygen, that basically makes it so, you know, you put in X amount, you put in one certain part of RP1, certain part of LOX, and all of the liquid oxygen will combine with all of your RP1, and you'll make a more efficient explosion. The problem is, like, when you do that, you're introducing a ton of heat. You introduce a ton of heat into the design. That's called running stoichiometric. Remember when we were playing Summer Car FlyKin and I had the wideband sensor and I was trying to get it to read 14.7? 14.7, stoichiometric for air to fuel ratio on an automobile. This thing is still combusting things at the end of the day. It's just not combusting air. Why? Once again, no air. So that's why rockets bring the liquid oxygen with them. And FlyKin, I know you know this. I'm just kind of explaining it so everybody else knows. So you adjust the mixture rate on your gas generator. You run fuel rich. They spray a ton more fuel in than oxygen. One, that makes all your oxygen basically combined with all your fuel and then have leftover fuel. Right? What happens to that leftover fuel? Well, believe it or not, I don't know if you guys ever driven around a gasoline powered car. Gasoline can absorb a lot of heat. RP1, diesel fuel, they can all absorb a ton of heat before they explode, right? So they run the turbine machinery here, the gas generator, they run it fuel rich, very fuel rich. That keeps it cool. Keeps it nice and cool, right? And make sure it doesn't melt your turbine machinery. Your turbine machinery needs to stay cool. All that extra fuel that they introduce into the gas generator absorbs the heat given off from the combustion to turn that turbine. So now you have a lot of heat that's relative. You have a lot of RP1 that's relatively cool being shot into this manifold right here. That RP1 film forms a nice layer of film insulation on the inside of the nozzle. And that protects that part of the nozzle from the heat that's driven from the main combustion, the heat that basically comes out of the jet from the main combustion chamber. It's called film cooling. That's what this is. That's why this part of the nozzle right here is nice and cool. The film cooling and the alloy radiative metal that's going on with the nozzle is enough to get it so this nozzle, which is getting extremely hot, doesn't melt. Because shedding heat in a spacecraft is really difficult. That's one of the hardest things to do. Everybody says space is cold. Space is not cold. Space is nothing. Space is the absence of heat. Because there's the absence. There's no matter. There's nothing up there. There's just light. Right? So light is the only way you can really get rid of heat, because you can radiate heat through light. You can't, I mean, you could convect heat through gas, or you could conduct it as well, right? Like the RP1, the fuel-rich mixture that's going through the gas generator is conducting a lot of the heat out, and that's getting dumped into the engine. Now, I know what people are going to say, well, isn't the gas turbine exhaust hot? Well, yeah, sure, of course. It's not as hot as what's coming out of the main combustion chamber of the rocket, now is it? Gives you a nice thermal medium. It's called film cooling and protects that part of the nozzle. So it doesn't overwork your alloys here, because your alloys are a passive system. The alloys are completely passive. You can only introduce so much heat into this thing before the nozzle starts to melt. Because once again, spacecraft in space, very hard to get rid of your heat. It's very easy to just build up a lot of heat. So like if you put a computer up in space, right, provided it was rad hardened and just left it there, it wouldn't freeze. It would melt. Yeah, it would melt. There's no way to get rid of the heat. So the computer would just keep conducting heat, and the computer would get hotter and hotter and hotter and hotter until it just melted itself. It can only absorb so much heat. Bang and blow. Hey! Yep, right. World's best thermos bottle. Vacuum insulation is the best type of insulation, right? Mixture ratio. You said mixture rate. It's just mixture. You could just call it mixture. Excuse me. So, yeah, that's turbine machinery. That's the dump from the gas generator from the Merlin vacuum. That's film cooling the nozzle. So what about this part? I swear to God, if you point at that stupid recirculation pipe, I'm going to slap you. I'm going to slap you. I don't know what that does. It's a pipe that does magical things, okay? Do we think that SpaceX tore down the huge long tank at 39A to have horizontal tanks instead, like at Starbase? Maybe spherical tanks? I don't know, Hampus. I haven't really seen much. Yeah, I don't know what this is. It's something that's connected to the turbine machinery that gets hot. I have no idea what that pipe does. I don't work for SpaceX. I know general principles of operation. If I knew what that was, I probably wouldn't be able to tell you anyway. That is the lower chamber hot pipe. It's for getting hot. It is for getting hot and transferring some sort of fluid. Ah, yes. The hot pipe. Anyway, a little bit on gas generators there too, just in case anybody was wondering. Okay, that's going to do it for the O3b MPOWER 7 and 8. I'm going to switch this over to space news, guys, if you don't mind. It's the hot pipe. That's the dingle bop, and it goes in the grumbo, where the fleeb's rubbed against it. It's important that the fleeb is rubbed because the fleeb has all of the fleeb juice. Then a salami shows up and rubs it, and then spits on it. They cut the fleeb. There's several hizzards in the way. The flamps rub against the jumbles, and plubis and grumbo are shaved away. That leaves you with a regular old plumbus.